Okay, so where was I? Oh, right, ignoring Angela. So let's get to, is that really how this live broadcast is starting? And we're back. And we're back. Honestly, I'm going to get fired one day. One day I'm just going to get fired. But until that day, we're going to do some chemistry. When you think combustion, probably you imagine, I would assume, what I imagine, which is you think of things exploding, right? You think of bombs, or you think of, like, whatever, something like that, which is true. That's the kind of reaction we're going to work with. But combustion is, generally speaking, if something is combustible, it doesn't necessarily mean it'll explode, but it does mean that it will, catch fire, and react with what? When something is catching fire, what will it react with? Oxygen. So specifically, sorry about this, when we talk about combustion, we're talking about the reaction of organic compounds or carbon-based compounds reacting with oxygen. So we're going to talk about hydrocarbons. And a hydrocarbon, as you can imagine, this is the foundation on which organic compounds, so like the things you're made of, are based. And based on the name, what are they? Some compound of carbon and hydrogen. And sometimes you'll see some oxygen in there as well. You can see additions to things, but the basis of it is carbon and hydrogen. If you think about it, you don't have to draw this, but if you think about it, it makes sense, because how many bonds can carbon make? 4, which makes it a very logical backbone for, hello, how are you?
Did you do your attendance?
Yes, I did. How you doing? How was your break?
It's good.
Good. Doing well, thanks. If you want to carry on with 4 you guys, that'd be great. So if we connected carbons together, if you just keep connecting them endlessly, you'd get this endlessly growing structure, right? That's what graphite is, but that's also what diamonds are, and coal, and all these things. But if you want to connect them and have it stop at some point, hydrogen is a really logical thing to bond with it, because how many bonds does hydrogen want to make? 1. So you can see that if you put carbon and hydrogen together, you can make a big molecule, but it also can be a molecule, bless you, that has a definite shape and size. Does that kind of make sense? This is the basis for all living things. If you take grade 12 chemistry, you'll learn about what we call organic chemistry. We'll start to talk about that. If you keep studying chemistry, you'll eventually get to like courses that are fully on organic chemistry, and those are like the Widowmakers. Those are the brutal courses. Those are the ones that make you cry. But when you start with it, it's actually really friendly stuff. It's not till you get more advanced into it that it gets kind of miserable. In general, then, what we're going to say is this: if we have some kind of hydrocarbon, and we react it with oxygen, and I'm putting question marks because you can't balance it unless you know what that hydrocarbon is, right? But if you react it with oxygen, what's going to happen? Well, why do things react with oxygen at all? Why is oxygen something that tends to react with things? You think of everything oxidizing, right? Like if you leave food out long enough, it oxidizes. It will make wine oxidize. Everything kind of reacts with oxygen. You leave iron out, it will rust eventually. Yeah. Very good. Oxygen, A, is present in high concentrations everywhere on Earth because it's present in our atmosphere. So it's always available to react. Beautiful. And then the second point is oxygen is highly electronegative. And when it's oxygen gas, it's in a pretty unfavorable relationship for itself, because as something that is very electron hungry, as something that wants to have a strong hold on electrons, when it's stuck to itself, it's stuck in a relationship where it has to share equally. So it is always sort of energetically favorable for that oxygen gas to break apart and bond to pretty much anything else, because with pretty much anything else, anything to its left on the periodic table, it's going to be in a relationship where it can hold those electrons more firmly. So oxygen gas is highly reactive, and exactly like Sarah said, it's highly present. We find it all over. So what does that mean? When oxygen bumps into this, so if we go back to, I'll draw that same thing we had again. When oxygen bumps into this, Can it bond to anything right now? Is there anything that has open spots available to bond? No. So it's going to have to break bonds. Does that make sense? For oxygen to bond with anything, it's going to have to break bonds. And in fact, if enough oxygen is around, it will break all of these bonds, and it will bond with everything, which means that hydrogen won't be stuck to carbon anymore. Hydrogen will be stuck to oxygen. And carbon won't be stuck to hydrogen anymore. Carbon will be stuck to oxygen. What are hydrogen and oxygen going to bond to form? So we rip that apart. Now we have a hydrogen here. We have an oxygen here. How many bonds does the oxygen want to make? 2. So it's not going to stick to one hydrogen. It's going to stick to 2 of them. And when it does that, it's going to form water. So all of the hydrogens from this are going to end up stuck to oxygen, and that means they're all going to form water. Now, how many do we get? Well, that depends on how many hydrogens we had to work with, and how many oxygens we had to work with. What about the carbons? How many bonds do they want to make? 4. How many bonds does oxygen want to make? 2. So what's that going to look like? They'll make a double bond. Okay. So now we have carbon and oxygen making a double bond. And another oxygen making another double bond. What compound is that? Yeah, CO2, which we commonly call carbon dioxide. Good. And of course, how many of those we will produce is just a function of how many we started with. So combustion reactions are actually very predictable because oxygen is so highly electronegative that as long as you have enough of it, everything will end up stuck to oxygen. And we typically have enough of it because, again, in our atmosphere, we have an ever-present, a functionally infinite supply of oxygen. Obviously, there's not actually an infinite amount of oxygen in the atmosphere, but there's a lot. Now, having said that, local to where the reaction is happening, does oxygen get used up? Of course it does. You've experienced this before. If you have a fire going and you want it to burn faster, what can you do with it? I'm lazy and I was never a Boy Scout, so when I light a fire, I get a little fire going and then I get my leaf blower and I just blow some oxygen, I just blow some air on it. If you do that for a little bit, it'll start, if you go too much too quick, you'll blow it out, right? But if you just keep a steady supply of oxygen going, you can get your fire to burn much faster, right? Does that make sense? So you can definitely use up the amount of oxygen available in a local space. But that's the basic rundown there. So let's look at one such example. We'll do one together, and then you can do one yourselves. The simplest possible organic compound. How many bonds does carbon want to make? 4. How many bonds does hydrogen want to make? 1, but you're on the right track. So the simplest hydrocarbon you could make would just be a single carbon, and each of its bonds would be to a hydrogen. Good. Very good, just like that. That is called methane. Of course, in the naming system, you know what would it be called? You're right, that's called methane, but in how we have learned to name covalent compounds thus far, what would we call this? Carbon tetrahydride. That's right. So carbon tetrahydride is more commonly known as methane. In fact, methane is its proper IUPAC name, but you'll learn that naming system next year, assuming you take 4U Chem, which you all should. It's a great course. So if CH4 reacts with oxygen, again, the oxygen is going to rip that apart, and what are our products going to be? Water, because all the hydrogen is going to turn into water, and carbon dioxide, because that carbon is going to turn to carbon dioxide. And then all you have to do is what? Balance it. And so let's look quickly. How many carbons over here? Just 1. How many over here? 1. So how's carbon doing? Good. How many hydrogens here? How many here? 2. What can we do? We put a 2 in front, and now the hydrogens are cool. How many oxygens? 1, Well, let's look here. For oxygen, we have how many here? 2. And how many here? For a total of 4. Very good. What about over here? How many oxygens? 2. And so what do we need to do? Put 2 in front, and that will make it 4. And now we are balanced. How's that feel? Not too bad? Now that's a nice easy one. But complete combustion, bless you. Always produces H2O and CO2. All you have to do is balance it. So, with that in mind, I would like you to make an attempt to give me the balanced chemical equation for the complete combustion of pentane, which we would know as pentacarbon dodecahydride. Pentacarbon dodecahydride, but more commonly known as pentane. I'm going to give you, 5 minutes to work on that. If you need help, let me know. But I don't even think you'll need 5. I think you'll have it done before that. But I'm going to quickly pop my head in next door and say hello to Mr. Calford. I'm going to come back. If you're not sure what to do, talk to a friend. Talk to Ruby. Talk to yourself. That's what I do. Okay. Scintillating conversations. Hello. How you doing? Yeah, what's up? Oh, boy.
Don't forget everyone who fed you. I think my phone did a little concern.
So he said, how much you have for me. So this be like,
just start by writing out H2O plus CO2. Because that's what it's going to react with, and then you add the numbers. Because those are the compounds that it releases, and now you can put the numbers in.
okay.
Dude, yesterday was so fun.
You done?
Yes.
You got this? You?
I was freaking fine. I got like 28 kills. We played Kojima as well, you remember that? Where it's the three in the back. Because there's 2 people hitting.
Yeah. I'm just
Just do it at home. It's so sad doing it. I hate data. Like I'm never gonna. The thing is, it feels like such like a big learning curve. I feel like I'm never gonna be able to get good enough at it to actually do it. Scroll. You rat.
Sarah doesn't have to listen to it. She's not walking. She's feeding her chair.
I'm sorry. What?
I've never said anything like that. Well, next season.
Of course.
Sarah, really just like,
Dude, I actually moved so like I didn't get my hips up before. Yeah, the last time was a lot better than
This girl broke my spine and didn't realize. She's like, oh, I didn't go to the pain. That's terrible.
Why are you looking at my answers? 8 times 2, because there's 10 oxygen here, 6 oxygen here, 16 total. 8 times 2, 16, 16 oxygen. What did you get?
Talk to me, team. What's our balanced chemical equation here? Go.
alright, so it's gonna be like a C5H12.
It's going to be like that, or it's going to be that?
It's going to be
Okay, just checking. C5H12.
plus O2,
Okay.
and then you like do that on the other side.
Yields.
Copy like the C5H12 plus the O2 on the other side.
Yeah.
And then you have to wait.
Yields. That's what you can say for that. You can say yields. And
Yeah,
then,
you
yeah.
have to put H2O plus CO2.
Okay. This accent is really flowing. I like it. It's really like, who knows where we're going to land next. It's like a tour of the world in one answer. I like it.
See that C4H12?
Yeah. Okay, so how many of everything do I need?
You're gonna leave the first one alone.
Okay.
Don't even bully too much. And then you're gonna be like, since you need to balance the C's on both sides,
Mhm.
put a 5 in front of the CO2.
Nice. So now we have 5 carbons and 5 carbons. Beautiful.
Alright, and now we need to balance that crazy H12.
Yeah.
So I want to go crazy with the O's. So we're gonna put a 6 in front of the H2O.
Do I have to go crazy or am I good?
You're crazy.
Okay.
Alright.
Crazy enough.
And then when you look at the O's, right?
Ah! Perfectly dignified sound. Never mind.
Alright, when you look at the O's, they're a little uneven.
Sure. How many do I have here?
You have like
10.
6, yeah.
And how many here?
6.
For a total of?
60.
Okay.
So when you take 16, you cut that in half. Thank you. You get 8. The numbers, no.
That was funny. Come on.
No.
Come on. That was pretty good. I cut it in half and then I put it here. So I need 11. See?
Second
I thought that was pretty good. Okay, never mind.
I have no idea.
Cut it in half, and what does that look like? It looks like an 11. That's what it looks like. Yeah. Okay. I thought that was funny. Anyway, fine. Unappreciated in my own time. Okay, so how many do I need? 8, I believe, is correct. Okay.
Put that hair down.
Yeah, that looks good to me. Right? And then we have 5 carbons and 5 carbons. And we have 12 hydrogens and 12 hydrogens. You talking to me?
No,
Okay.
you're not doing that.
Well, that's why I was confused. Okay. How's that feel? Not too bad? Okay, now this means that any organic material, when you burn it, should produce what two things? Water and CO2. What comes out of the back of the tailpipe of your car? Assuming you have a gasoline-powered vehicle. I mean, if smoke is coming out of the tailpipe of your car, you probably should take your car to a mechanic. I can tell you from hard-won experience that sometimes you think it's not a problem, and then your car bursts into flames. So
you have the most specific space.
that's a true story. I was moving. It was the day before my wedding.
Yeah. Oh, they were sure you
I was literally moving. My car was piled full of everything I owned, and then all of a sudden it was whoosh in flames, and all my stuff burned. I lost a guitar. I lost all my clothes. I lost about 2/3 of my CD collection. Like my CD collection started at like the letter like N after that. What else did I lose? I lost a vegetable tray. That was supposed to be for the rehearsal dinner that night. I lost a pile of cash. Yeah, I lost a lot of things. Anyway, point of the story is, if there's black smoke coming out of your tailpipe, that's from, but usually what's coming out of your tailpipe? You'll get some things that smell because there's some sulfur in there, and sulfur ends up with oxygen too, so you'll get sulfur dioxide. Might get some ammonium oxides. But primarily, what should be coming out of the tailpipe of your car? Water and carbon dioxide. When we burn sugars inside our body, what do we produce? CO2 and water. We breathe out CO2 and we just use the water systemically for ourselves. When you burn a log on a fireplace, what do you get? Water and carbon dioxide. We're not used to thinking about that, but it's true. If you put like a glass mirror or something above a flame and put like some ice on top or whatever, you'll get condensation on it from the water coming off of the flame. Because when you burn things, you produce CO2 and you produce water. But you know something else. If your car, and this happens less often now, but some people do this to their cars intentionally. These guys who love to have big plumes of black smoke coming out the back of the car. They modify the injection system on their engine. Stupid. But if your car is mistimed, and that used to be more of an issue back in the carbureted days when things weren't computer controlled and fuel injected, sometimes you see black smoke coming out of the tailpipe. What is that? Or when you burn a log on your fireplace, it probably doesn't totally disappear, just producing carbon dioxide and water. What's left behind usually? What? Ash. And what's ash? What's ash? This is carbon. Sometimes you'll have coals left behind. What's coal? Carbon. And there's a dangerous chemical that can get produced when you burn something. If your furnace is misoperating, or if your car is misoperating. Not carbon dioxide, that will always get produced. Methane, yeah, if it's just not burning at all, then the natural gas can just get released as methane, which is dangerous. I heard someone say it. Carbon monoxide. So if it doesn't burn at all, you will get you'll get the methane or the propane or the butane or whatever it is released. But what can happen is this: we run out of oxygen. For a car engine to burn without producing any smoke or without producing carbon monoxide, it's imperative that enough air get injected with the fuel so that when the fuel burns, it burns completely. If it doesn't, you'll get carbonization, which means not only will you get black smoke coming out of the back, but you'll get scoring, you'll get carbon, like soot, forming on the inside of your pistons. And that's not good for your car, right? That'll interfere with the rings, that'll interfere with the timing, and eventually it'll lead to reduced efficiency. You got to make sure there's enough oxygen. But if there's not, the reaction can still happen. So even if there's not enough oxygen available to completely rip things apart, what oxygen is available will still rip things apart. Does that make sense? And that can lead us to something called not complete combustion, but incomplete combustion. When there's insufficient oxygen, hydrocarbons will still react with what oxygen is available, but they'll form some combination of carbon dioxide, carbon monoxide, and solid carbon. All of the hydrogen will still end up bound to oxygen. Does that make sense? Hydrogen is a better bonding pair for oxygen because the bigger difference in electronegativity there. So you'll always get water, but sometimes we will also get some carbon monoxide forming, which is a big problem because carbon monoxide is extremely dangerous. Does anyone know why? I gave myself carbon monoxide poisoning by accident once. I'll tell that story later. I don't think I have time now. Yeah. It's odorless and you can't see it. But why is it dangerous at all? Like carbon dioxide is dangerous in as much as if there's way too much of it in a room, we can have trouble getting access to oxygen. But there has to be fairly high levels of CO2 for it to be dangerous. Carbon monoxide, on the other hand, a very small amount of it can be deadly. Why? Yeah. It actually isn't reacting with anything in your body. I mean, I guess you could say it's reacting, but it's not really doing a chemical reaction. It's binding to something. It doesn't bind to the oxygen. The problem is not that it binds to your lungs. It gets into your bloodstream. It binds to hemoglobin. What's hemoglobin?
The thing in your red blood cells that processes oxygen.
Yeah, that binds to oxygen. Hemoglobin is the molecule that pulls oxygen out of the air and binds it in your blood. And that's important because it means that the oxygen in your lungs is constantly being removed, which means it keeps wanting to flow out. It allows oxygen to diffuse into the blood. If you didn't have a chemical to carry it, it would just, a little bit of it would make its way into the blood and they'd equilibrate, and then the most you could ever do is get half of the oxygen out of the air. Does that make sense? And in practice, you wouldn't even get anywhere near that. But hemoglobin keeps pulling the oxygen right out of it and binding, which means the concentration of oxygen in the blood is actually always zero, or close to it, because it's being bound up by hemoglobin, which means that as far as diffusion is concerned, the oxygen just keeps diffusing into the blood, so it's incredibly important. The problem is that carbon monoxide is what we call an antagonistic inhibitor. Basically what it means is that hemoglobin likes carbon monoxide a lot more than it likes oxygen. In fact, hemoglobin will bind to carbon monoxide about 1,000 times more often than it will to oxygen if you have equal amounts of the two. Which means that even if you have just 1/1000th as much carbon monoxide in the air as oxygen, you're going to be at 50% oxygen saturation, which is deadly. Your body can't survive that. So in fact, once you get within the range of about 1/10,000th as much carbon monoxide in the air as there is oxygen, your blood oxygen saturation drops to a level that you suffer hypoxia. Your brain just can't get enough oxygen, you go unconscious, and you'll die. So that's not good. We don't like that. So carbon monoxide, very dangerous. This is why we should have a carbon monoxide detector in your home. If you don't have a carbon monoxide detector in your home, you should go and buy one immediately. It saves lives. People die of it all the time. Carbon monoxide can be leaked into your home a number of different ways. A malfunctioning furnace, if you have a gas fireplace, that malfunctioning, but it could be any number of pieces of equipment running. If you have a gas stove whose pilot light isn't functioning properly, any kind of things like that. And it can be very, very dangerous. So that's my public service announcement. And I can tell you from hard-won experience, I guess I will tell the story. I was renovating a basement bathroom once, and I'd rented a concrete saw because I had to cut the floor out because I had to run all the plumbing because there wasn't a bathroom there. I was installing a bathroom. So I had to cut big trenches in the concrete floor of my basement. So I'd rented this electric saw, and it kept tripping a breaker. Even though the line was supposed to be rated, so I plugged into a different line, it was tripping that, and I was getting really frustrated. So I took it back, got another one, it was doing the exact same thing. So I got frustrated, I took it back, and I rented a gas-powered one. And I opened a couple of windows and things like that and started doing this. Unbeknownst to me, my wife was like, oh my gosh, this is kicking up so much dust. And I don't think she had realized that I had rented this gas-powered one. So she took it upon herself to close all the windows and to tape up the doorway. So that the dust wouldn't get everywhere. So I was cutting this floor out, and all of a sudden at one point I made this cut, and this big section of floor that I was working on fell in, which is good because then I could break it up with the jackhammer and get doing what I was doing. And then I just kind of fell over. I was just lying there, and I realized I couldn't lift this thing up off of me. I was just kind of too tired. I just wanted to go to sleep, and then my wife came down and found me with a still running saw on my chest and lying all there, and she was like, Joe, are you okay? And I was like, I feel great. I'm just going to go to bed. And she was like, I don't think you should go to bed. And I was like, I think I should. It feels really appealing right now. So then she dragged me out onto the driveway, and she had an oxygen mask in her car because she's a midwife. So I was lying there with an oxygen mask on, like lying like this on my driveway. And my dad came to visit with like one of his friends, and they're like, "What are you doing?" I'm like, "I'm good. I just need a nap." And it was like, "You're not allowed to sleep." And she was like slapping me to keep me awake. And then later that night, I had a gig. So my friend Tara and I were playing this like it was like a I don't know if you call it a shower, but like it was people who were getting married like on some like destination wedding, but before they went to get married, they had just like a little kind of party for people who couldn't go in their house. So we were playing this gig, and like I couldn't even like lift the speaker up to like put on the stand. So I was like, "Are you gonna be okay to do this gig?" I'm like, "I'm fine. I feel good. I might nap in the middle." And she was like, "You're not allowed to nap." So then apparently, according to her, it was terrible because I was playing at like 1/3 speed and just playing like incredibly slowly and laconically the whole time, and it was awkward. I have no memory of that. But anyway, the point being, don't give yourself carbon monoxide poisoning. And if you're going to operate gas-powered tools, make sure you do so in a well-ventilated area. Because if you don't have enough oxygen present, truth is, if machinery is running perfectly properly, it should not produce any carbon monoxide if it's getting sufficient oxygen. But the reality is that that's rarely the case, which means when we burn hydrocarbons, we will usually also produce some carbon monoxide. And if oxygen levels are really low, you'll even produce some solid carbon. Yeah. Yeah, so in that case, you're not releasing carbon monoxide, you're releasing the methane itself, like the gas that's in there. Now, that's bad too. Methane is also an antagonistic inhibitor of hemoglobin, not nearly as bad as carbon monoxide. So it's not nearly as immediately deadly, but it absolutely is, it will do the same thing eventually. So eventually, if you let that be open long enough, you'd be feeling lightheaded. And people have died that way too. So you want to be careful about that. The other thing to note is that carbon monoxide is a terrible greenhouse gas. I mean, the other thing is, hypothetically, it could be explosive. The reality of the matter is you're not going to have it mix. You're not going to get enough of it released that it would mix with an appropriate amount of oxygen to explode unless things were in really, really, really dire straits. That's kind of movie stuff. You have to release a lot of natural gas before there would be a sufficient amount of it to sort of mix with the oxygen in the room and be explosive. It's mostly going to diffuse enough that even as it burned, it would do so in sort of a quiet, explosive manner. But also, terrible greenhouse gas. So you do want to be mindful. I was always a gas stove guy because I learned to cook in a restaurant kitchen, and so I'm used to that, and I love it. But I will say that I'm planning on my next stove to actually go with an induction cooktop, which I think is a nice system. But environmentally, those gas stoves are not very good for the environment, but also the air quality in your home. They are, pointedly, if you live in a house with a gas stove, the amount of oxygen relative to CO2 in your house is measurably lower, and that's not good for your long-term health. So that's my public service announcement. Having said that, it is a nicer way to cook. So, it's a question of your priorities, I guess. Yeah.
Make sure you change the batteries on your carbon monoxide.
Yes.
Detector,
Yeah.
Because some of them will just beep as if they're going off when they're low battery.
This is true.
And then give you a heart attack.
And don't throw a frozen ham at your furnace,
That's right. What?
My mother did that.
Hi.
I know you have a bunch. The plastic little.
Yeah, a million. Just in one of the blue bins straight ahead, they're in little plastic wraps. If you can't find them, just shout.
Just show.
Just shout. Just be like, "Oh, lay down!" And I will come find them. Just like that. Was that good? That was good, right? Okay. So generally speaking, with incomplete combustion, you're going to start with the same thing, some hydrocarbon, and it's still going to be reacting with oxygen. But if there's an insufficient amount of oxygen, we'll still get some CO2, but we might get also some carbon monoxide, and we might also get some pure carbon. And of course, what will the hydrogen form? Hydrogen is going to form into water. There's no such thing as monohydrogen oxide, HO. That doesn't work. By the way, if you try to draw how carbon dioxide or carbon monoxide works, the first thing you're going to notice is that it looks like it doesn't, right? For the very formation of carbon monoxide It's a weird chemical. It's almost half ionic. It involves a transfer of an electron as well as this covalent bonding, which makes it not a very stable substance. Carbon monoxide will readily react again if it can. But just to be aware, as of right now, if you tried to, I would never give you a question where it was like, draw me a Lewis structure of how carbon monoxide forms, because it would look like it can't. Just a good reminder that chemistry breaks its own rules sometimes. Take grade 12 chem, and you can learn about how it works. Now, what that means is that there's no one right answer. There's actually an infinite possible number of ways this can go. Does that make sense? Complete combustion, there is only one way to do it. Incomplete combustion, there's always an infinite number of ways it could play out. So I can never say what is the equation of an incomplete combustion. I can just say, what would one example be? Does that make sense? We're going to, yeah. Yeah, so the answer is, in terms of, in the real world, the way you'll know is if it's producing carbon monoxide or if it's producing solid carbon. So for example, if you ever burn sugar on the stovetop, if you burned that sugar with enough oxygen mixed in, it would just disappear completely. Carbon dioxide and water. But if you've ever burned sugar in a pan, the thing you've almost certainly noticed is that that's not what happens. You get this black carbonous mess, right? That's because you couldn't get enough oxygen into the middle of that. So all of the sugar that was in the middle of that substance combust incompletely. In fact, so incompletely that it just formed a big carbon mass. It got enough oxygen to get the hydrogens out as water, and it just left behind the carbon as coal, right? Basically a lump of coal. You could burn that lump of coal, it just takes much more temperature. So if you actually heated that up enough, you could actually get that to catch fire and turn into CO2, but you'd have to give it oxygen. Did that answer your question? Now, in terms of when it's a question on a test, I'll just tell you. I want to know the complete combustion or the incomplete combustion. I might even say, give me one of each. Tell me the complete combustion. Also tell me one possible incomplete combustion. But yeah, if it's a test question, I might design a test question to be like, with some hints in it. Like, your furnace is functioning properly and there's no carbon scoring and your carbon monoxide detector isn't going off. What would the equation of that reaction be? Or I might say, your furnace is malfunctioning and as a result your carbon monoxide detector goes off. What's one possible reaction that could lead to that? And that would be the hint you need to know. Hi, come on in. Hello. Sorry? Hi, come on in.
Would you like anything from coffee card?
Oh, I would love a coffee. Yeah.
You don't love it?
No, not today.
Wow. Just
That is crazy. Everyone is like, you remember how Mr. Lush got us to crack our knuckles when he came in?
what?
You know,
I'm not even.
oh, you remember when Mr. Lush got us to crack our knuckles when he came in?
Yeah.
So if we come out, we should do it again. Frank, did you crack your knuckles recently?
That is a coffee cup and a sweet gig.
Well, I just cracked all of them.
The last 3 times I've come by, I've been doing a lab and I've been sad. But today, it was perfect timing because we're not doing a lab and I just emptied my cup. All right, so let's do one example here. And again, the thing you have to know about this is there's no one right answer. So we're talking about ethane, which, what would our naming for this be? Dicarbon hexahydride. So if we take dicarbon hexahydride and react it with oxygen, again, all that hydrogen is going to turn into what? H2O. But then we could potentially get a single carbon monoxide and, while we're at it, a carbon dioxide. That's a possibility. And then we could just balance this. I've specifically kind of chosen it so that the carbons balance, right? That makes sense? So 2 carbons. How many hydrogens do I need? 6 hydrogens. How many do I have here? 2. So what can I put in front? 3, which means that now instead of 2 hydrogens, I have 6 hydrogens. So now our carbons are good, right? We have 2 carbons and 2 carbons. Now let's count oxygens. How many do we have over here all together? We have 3 from here, and then 4, 5, 6. Right? How many do I have here right now? 2. How can I remedy that? Put a 3 in front, and that would give us 6 oxygens. Oh, thank you so much.
You're welcome.
Appreciate it. It's lovely. Lovely cup of coffee.
Is that one even done?
Yeah. Like I said, perfect timing. Perfect timing. So that is one possible incomplete combustion. But again, this is just now an open thing. You could do any you want. So I want you to take 2 minutes and come up with your own. And when you get one that works, and listen, get creative here. Go nuts. Is there anything stopping us from putting 11 here and having 22 carbons to work with? No, go nuts. Is there anything stopping you from putting a 7 here and having 14 carbons to work with? No, you can balance this any way you want as long as it balances. With incomplete combustion, there's an infinite number of possible combinations. So there's no one right answer. Can you always do the super lazy, just balance the carbons with pure carbon, and then just take care of the waters? Yeah, nothing's stopping you from that either. You can use water to take care of all your hydrogen and just throw a C there to be carbon. That's okay. Now, it's boring, but don't let me stop you. Yeah. Maybe. Do the numbers add up? I'm not necessarily able to do that math in my head, but as long as everything balances at the end, it works. There's no wrong answers if everything is balanced. You got one? Can I see? Yep, that works. Make me another one. Yeah, sure. Kayla, you got one? No. Get on it. Get going. Fight with it. Don't wait for me. Yeah, nobody wait for me. That you're not helping yourself if you wait for me. The whole point is for you to do it. Yeah. Yep. What's that?
Would there be a situation where oxygen is alone?
No.
Okay. I made it too complicated for myself. Would it have a half of oxygen?
They actually do allow that. They actually do. So if you need 3.5, now they would write that as 7/2, not 3.5, but yeah.
Okay.
They use the
So do I put more than 7?
yeah. So if you need 3.5 O2s, basically how many oxygens you need total, just put that over 2 and you're good.
Okay.
How many oxygens are on your right side? That actually is permitted. I was going to teach that next.
39.
So it'd be 39/2 O2s.
Okay.
Yep. Yeah, if that's all you have, that's love. It's all good except that arrow.
What's wrong with the arrow?
Exactly.
It's right there.
It looks a little bit like those things like knights joust with.
Arrow. Interesting arrow.
Sarah,
No.
Sarah, excuse me.
16s.
No, don't touch me. Don't touch me.
Here.
Don't touch me. A question that I was extremely confused by. What do you mean, like, this? Is it like,
It just means that
there's three?
it just means that there'd be two answers because Mercury can actually form two different. I'm just telling you which one to use, so you don't have to give me both answers. If you want to give me both, go nuts.
Oh, I was going crazy. Also, what is that? I searched it up and it gave me like this.
Yeah, thiosulfate S2O3. What charge does it take? -2. So you're good.
Okay.
Yeah. I do.
Oh.
When you think you've got a good one, come put it up on my tablet. Oh, that's adorable.
I wake up to disaster because that's the question cosplayer.
See any great cosplay while you were there?
There was quite a few really cool ones. This year is dead this year. Like I bought the past 2 years.
Yeah.
And this is my 3rd year. And I was worried because there's like panels and stuff.
Yeah.
There was 2 panels per day we wanted to go to. Normally there's like 7. So that wasn't a great time. Huh?
That's wild.
Yeah. It was they cut down.
Yo, change that arrow.
I'm not changing anything. My arrow is beautiful.
Okay, just so you know, sorry, the way we write it, I might have misseen. Sorry about that. So how many is it? 34?
39.
So sorry, we'd say 39 over 2 O2s.
Okay.
Hey guys, this is actually a good one. And I gotta be honest, I'm changing your arrow. I can't take it. It's just I can't handle it. I can't handle it. I'm sorry.
That is an arrow.
Welcome to the club.
Sarah, where's
I mean, Max, listen to me. Listen to me. Your club is a different club. All right? The club, and listen, this is good. You're not only a member, you're also the president. Like, it's a different club. Okay, listen, shh, look here. Now that it has an arrow that isn't causing me to fibrillate,
Hope it hurts.
wow. I feel so attacked. Okay, but I love, Sarah went hardcore. Sarah went for a tough one. She gave herself 7 of these to work with, which is 14 carbons. She had 8 of them form a CO2. 2 of them form carbon monoxide, which brings us to 10. 4 of them form pure carbon. Because she had 7 times 6 is 42. So she needed 21 waters to take care of that. But the result of that is she has 21 oxygens, 2 more for 23, and then 16 more for 39. Now, you normally would have to multiply everything by 2. In combustion, there is something we allow. We permit half oxygens just for brevity's sake. All right? So the reality is that, of course, you can't have half an oxygen molecule, right? So the reality is, what do you really have to do with this whole balancing? you really have to multiply everything by 2. But for brevity's sake, they permit us to just say 39 over 2 oxygens. It's kind of like a little bit cheaty. It's a little bit sort of cheating the system, but it's permitted. Does anyone else have one they've come up with they want to put up here? Yeah.
What other charges? Mercury has a charge of 2. What other charges have? Because the periodic table has 2.
Mercury is actually a weird one. Guys, well, whatever. Everyone can look at this. If you're working with Mercury is strange because there's the Mercury plus 1 ion, and then this is actually really weird. Mercury 2 is actually a diatom of this. It's Hg2 plus 2. For now, if you just treat it as Hg plus 2, I'm not going to penalize you because we haven't worked with this. So it is actually a diatomic ion. It's actually a radical in its own right. Because these two mercuries are stuck to each other, not when they're by themselves in this case. It's not diatomic when it's alone. In fact, mercury left by itself can form, if we dissolve it in water, the mercury 2 plus ion, which is 2 mercuries stuck to each other with a charge of plus 2. Again, for now, if I told you to use mercury 2 and you just treat it as being this, I'm going to give you the marks because we haven't taught you this, but this is the actual correct thing to do. So if you Google it, that's what you'd find. It's a diatomic ion. Anyway, you don't need to worry about that. Anyone else got a incomplete combustion of ethane they want to share? Anybody? Got an exciting one? All right, I'm going to treat this as something you know then. Easy to work with. Now, tomorrow we're going to do our next lab. What type of reaction are we up to? In our first lab, we looked at what types of reactions. You, phone in the box. Finally caught you out front. I was too lazy to walk over there earlier. I might keep it all day if I feel irritated, by the way.
Is this the box now? Or is like this one?
Whatever. So, no.
It fits pretty good.
Excellent. Nobody asked you. Okay, listen up. So, that came out ruder than I meant it to.
It always does.
I know, I'm sorry. What I meant by that, I just meant like I'm picking on him enough, he doesn't need your help. But that came out ruder than I meant it to, so I apologize. I'm sorry. Okay, look here. I'm abashed. I'm not trying to be rude, I'm being... I'm just born that way. That's a good question. Are rude people made or are they born? Nature versus nurture. I think it's more of a nurture thing. Anyway, I blame my mother.
Okay.
But don't tell her I said so. She'd hit me real good. Okay, so look here. Your lab books are back there. Return to you. Tomorrow we're doing a lab. Don't worry about the fact that they call it Lab Investigation Part 1. I just shamelessly stole this lab from a different source. It's cited somewhere. But in the meantime, listen. When we come to safety precautions on this particular one, we're going to be working with relatively concentrated hydrochloric acid. Everything else is very dilute, which means everything else we're working with is good and safe. All right, we've got no major concerns on this one. But we're doing what kind of reactions here? If we're creating an activity series, what kind of reaction are we doing? Single displacement. By the way, this unit is going to be done by the end of this week. We might even test by the end of this week. Latest we will test is the first day of next week. What should you be doing in the interregnum? Lots of practice. Again, this course is less about studying and more about practice. I mean, I guess you can think of those two things as being interchangeable, but specifically it's that skill piece. So if you go on the chemistry practice app, you can go to reactions and you can say, hey, I want to make sure that I'm comfortable doing single displacement reactions, even if they include basic radicals, even if they include difficult radicals, even if they include multivalent metals. And like right now, you can even set it so that it never gives you the formula, it gives you the name. And if you want to make sure that you're just getting practice with single displacement, then set to single displacement, right? Why it keeps putting that bracket in there, I don't know. I screwed something up. Yeah. Sorry? I should mention, I finally hung up these mailboxes I got forever ago. Now, going forward, anytime you want to hand something in, there is a very conveniently located period 1 hand-in slot where you can put that. There's also period 1 handouts. And for now, I'm going to mount, I need to order some narrower ones to go here, returns. So for now, if something is to be returned, I'm going to put it upright here. And if it's the notes, I'm just going to put this way. Does that make sense? Please make sure you keep it neat. So yeah, if you're handing anything in, right here. Right here is good. Yeah. Need my red pen.
Wrote in red and then you put their red.
Oh, did I not put your mark in? Sorry about that. It's right there. Do you want me to do it or you got it?
I got this.
Okay.
It bothers me.
Yeah, that would bug me too. Sorry about that.
Mark the other one.
I'm just going to mark them together.
Okay.